Ladies and gentlemen, first I need to say that it's a real great honor for us to be standing on this stage and be invited to address this audience on our favorite topic, SMR technologies. We'll do this as a shared presentation. I'll do the first part and then give the floor to Anicet. Context and introduction. Yes, I need to push on the green button here. So, first as a word of introduction, we are standing here on this stage today because in our company we have over several years studied SMR technologies intensively. We have engaged with several SMR developers of technologies that we believe will be have the potential to be real game changers in the future. And I guess it's 9 months ago that we met with Fermi Energia, and immediately we saw that we shared the same vision and the same analysis, being first enthusiasm for SMRs as a potential solution for future energy, and in the same time as well, the same concern and the same awareness of the huge challenge that is ahead of us in terms of converting our energy systems from this. So this is the challenge of the century. This is the challenge of this decade, to put in motion the solutions to actually giving up our addiction to fossil fuels, which today constitute 80% of primary energy, to carbon-free energy, as committed by Europe for by 2050 to achieve carbon neutrality. And we know that achieving such an objective will require massive amounts of energy, carbon-free, and available on demand, and very reliable. We know that renewable energy alone will not achieve this goal, and so nuclear power must be part of the sustainability equation, the long-term sustainability equation. Safe, affordable, sustainable nuclear. When we talk nuclear, we first have in mind the current construction projects. So Generation 3 reactors, for those who don't know, were developed in the 90s, tended to be of a very big size. This EPR in Olkiluoto 3 in Finland is a 1.65 gigawatt electricity. Contract was signed in 2013. Contract was signed in 2003. So you see the huge construction time and actually construction delays. These are due to the size of these reactors, power plants, and complexity. And this complexity has rippling effect everywhere, on the design, then on the licensing, then on manufacturing and construction. It breaks my heart because I worked on this project, I worked on other projects, and there are people in this room who can indeed share the same experience. Unfortunately, those very large projects could not be built in some cases, or have taken huge delays and cost overruns. On top, they are not adapted to smaller grids, and they are not very flexible. So, too bad, but we need to move to the next generation or to another solution. So, what are the conditions for new nuclear to become successful? We have pictured it in this slide in the form of three conditions of success, or three main challenges. The first challenge is recreate an appetite for investing in nuclear. And that goes with smaller size, smaller capex, smaller financial risk, better certainty on manufacturability, shop manufacturing, shipping to the site, shorter construction time. That's absolutely necessary, otherwise the financial burden of covering the risk is just too big. Second challenge is recreate trust in nuclear safety and be able to demonstrate that the new solutions will definitely avoid or eliminate the risk of accidents which have occurred in the past. The third challenge is being able to play a significant role in the zero carbon transition that I talked about. In a new energy system which will have a lot of intermittent energy, so flexibility will be required, and also beyond electricity, there is the need to decarbonize other sectors of the economy, industry, right? The fourth challenge is to be able to bring a convincing solution for long-term disposal of nuclear waste. And so solutions exist, so it has to be demonstrated that there will be a final disposal of such a waste, or even better, recycling of such waste. So the SMRs bring convincing answers to those challenges. To the first one, by standardized modules, reduce project size. We'll elaborate on that. In terms of the nuclear safety, passive safety, meaning the forces of gravity and physical laws, and sometimes even better, intrinsic safety, meaning that the laws of physics preclude accidents to occur. It's impossible to have a core melt accident. And also, by consequence, there will be no need for additional safety systems, which have a cost. There will be no need for evacuation plans for large areas around the plant. SMRs bring that advantage as well. And in terms of the third challenge, it will be required to have very flexible machines, being able to adapt and load follow according to the power demand, and to fulfill the needs for non-electric applications. And finally, reduction of nuclear waste. Some reactors, fast spectrum reactors, have the capability to work on used fuel and to virtually eliminate long-lived radioisotopes. This is just one example of this revolution in nuclear safety by having the so-called concept of walk-away safety. If something happens, you don't require operator action. You don't rely on the AC or DC power systems. And there's no need for bringing additional water for a long period of time for long-term cooling. Triple crown safety as advertised by NewScale. And this is another illustration of the new energy landscape in which small modular reactors would play a role of providing electricity, but also variable electricity, storage capability, heat, industrial heat to an industrial complex, and serving the needs of cities. So the things have to be seen in that kind of ecosystem of complementary sources of energy. So what is the landscape today for SMRs? Well, it's flourishing everywhere in the world. So there are over 50 different designs of about 6 reactor families. So it's very diverse. It's not like buying a car from a pool of different brands, but that are all essentially the same machines in terms of functionality and design. We have a great diversity of designs among those 50 products. And of course, according to a particular need, in this case Estonia, there's a need to down select from those 50 designs. And that's exactly the question that will be addressed by my colleague now on providing this down selection methodology to zoom in on what we believe should be technologies to be pursued for Estonia. Thank you. Lisa?
So thank you, Philippe, for this nice introduction. I think now that we know a bit more about what are the small modular reactors, we can really dive in this comparative assessment study that we've performed, and that, as Philippe mentioned, looks at the landscape that is very big. We are starting from more than 50 design initiatives that are popping up around the world, and what we wanted to do was to answer to two questions. What are the design initiatives that are the most likely to succeed, to emerge from the market? And what are the most or the best fits for Estonia and for the Estonian energy future? And for that, we started asking ourselves also one additional question: what are the criteria for success for an SMR? So that's the starting point of our methodology. So as I mentioned, we started from 50 designs, and to those 50 designs, I mean, comparing 50 designs is an enormous task, and obviously not the best efficiency to deep dive in all of them. So we applied a list of exclusion criteria. This list of exclusion criteria was established in partnership with Fermi Energia, and we wanted to see, in fact, what are the technology or the real requirements that are required for an SMR to succeed and to be part of Estonia's energy future. So let me just cite a couple of them. I won't go through all the list, but the important one, we focused on, I would say, small modular reactors, but not the very small, so not under 25 megawatt of power. And one important criteria we believe, and to emphasize what my colleague Philippe has said, is safety. And we put a very important criteria on being able to rely on passive safety. So the idea in this is really that for an SMR to be a game changer in terms of safety, you would like that in case, in a worst case scenario, something bad happen, the operator does not have to provide an action, at least for a period of time, extended period of time, and that was a strong requirement. So based on this, we were left with a list of around 13 designs. In fact, there is a 14th one, but I'll talk about this one afterwards. And we applied to this a high-level assessment methodology that is basically structured, so it's a scoring methodology centered around 7 technico-economic criteria that I will describe afterwards, and some preference profile to give weight to this criteria. In the end, we are left with a list of top-ranked designs, and as you will see in the presentation later on, there will be 4 that I will focus a bit more on at the end of the presentation, talk to you about what they are, why we think that they might be game changers, and why they might bring very promising solutions to Estonia. So without further ado, let's dive in. What are the critical success factors? What is necessary for an SMR to succeed? Well, in fact, what you can see here is that we summarize this into seven questions. So question 1, what is the ability of a design to be inherently safe and secure? So how can it improve safety? Second one, how is it to fit in tomorrow's energy market? And by that I mean that we know that the future will, of course, rely more and more on renewable energies, which are intermittent energy and so forth. In order to exist and to be competitive in this market, you need to be able to be flexible, being able to load balance, produce power when there is no wind, when there is no sun, but also to bring solutions where the renewable energies cannot bring solution. And by that, I have in mind industrial use of process heat, so the so-called process heat application, district heating, hydrogen production, petrochemical industries, etc. Third question, as my colleague mentioned, we are more and more worried about sustainability, and so we ask ourselves the question, what is the ability of a design to bring, to reduce waste generation and to bring long-term waste solution? Fourth question that is, again, quite technical question, how mature is the design? How fast can they deploy the reactor to the market? And what is the necessary development in terms of the supply chain to be sure that you will bring this technology to life? The fifth, sixth, and seventh are more, I would say, economical or market-driven criteria. Cost competitiveness, of course. I mean, I don't have to tell you that, but the environment is becoming more and more competitive, and even though we expect that there will be some cost increase, some system cost increase related to the renewables, you need to be able to compete in this market, and you need to be able to compete not necessarily with renewables, but also with gas and coal power. And then I would say the last two criteria, what is the ability of a designer to fund themselves to the development phases? I mean, developing an SMR design is not a small endeavor. It takes time, it takes money, some courage also, because there can be some up and down. And so we looked at what is the ability of a developer to get through these stages and really bring a product to life. And in the end, also what is the ability of a developer, their supply chain, their partners, to bring the reactor to life on time and at the cost. My colleague Philippe has mentioned the recent challenges of Gen 3 nuclear reactors, and especially the case of Olkiluoto, of Flamanville, and the AP1000 in the US. Those have been difficult times or difficult challenges for the nuclear industry. For an SMR to be successful, it needs to be able to be brought on market on time and on budget. So let's now dive in a bit into the results. I won't really focus on every reactor that is part of the study. As I mentioned, there were a list of 13. Those lists comprised five families of reactors: boiling water reactors, pressurized water reactors, high-temperature gas-cooled reactors, molten salt reactors, and sodium-fast reactors. So after this short introduction, I will give you an overview of what are the features of those reactors and how they fare in the comparative assessment. But what I wanted to show here with this picture was really how our methodology works. And as I mentioned, what we did was apply a score for each of the 7 technical criteria and apply a weight. What you see on the slide here on the big pie is the weighting profile that was kindly provided by Fermi Energia. So it shows what are the preference, where is the importance put in terms of criteria. I would say that this is a very a well-balanced weighting profile, but we still emphasis on delivery certainty. Again, putting the importance on delivery on time and on budget, on cost competitiveness, and on the ability of vendors to really be able to bring a product to market. So what you see here is that we have, when we apply this methodology, we have a ranking, an overall ranking of the design, and 4 of the design come out of the bunch, I would say, as very promising technology. There is a 5th one, which is DHT-RPM with a red cross, to anticipate on the question why is this technology selected and why, whereas it fares so well. Well, in fact, this design is a Chinese design of high-temperature gas-cooled reactor technology that is currently being built and that actually is under the commissioning phase right now, and that should start this year. It's the first land-based SMR that will be built in the world, and so we wanted to have this as a benchmark, I would say, because of course being able to bring a product to market is important. So we wanted to have this as a benchmark, but it was in fact excluded on the basis that bringing a Chinese technology that is quite new and that has quite some challenges in the Estonian market might not be the best fit. All right, so let's have a look at different weighting profiles. I won't go through all of them. If you have the feasibility study, you can find them on page 84 to page 86. But I just wanted to show different profiles where here we have a financial profile that put the emphasis more on cost competitiveness and how that impacts the results. You see clearly that some design that fared well in the other are doing less well in this configuration, and that's important. We wanted to show that, in fact, it's not only about scoring the design, you're a bit also comparing apple and oranges, and so the methodology and where do you put the importance matters. Same thing we see here on a profile called Eco-Modernist. So there the importance is, I would say, put more on aspects important to the public opinion. If I give an example, inherent safety, sustainability, and fitness into tomorrow's energy market are really important. And there again, we see a completely different results. What is important to see, though, is that if we apply a threshold, which is what we've done and what you can see in gray, the gray line on the graph, there are 4 designs, except with the red cross one. There are 4 designs that score continuously very well. Those are the NewScale reactor, the BWRX-300 reactor by Hitachi, the integral molten salt reactor by Terrestrial Energy, and the Moltex Energy design stable salt reactors. I will make a focus on this one in a few minutes. But before I jump to this, I wanted to give you a general overview of how, in terms of family of reactors, we see some trends appearing so that you at least have some understanding what you could see in the results. So basically, what we see is that light water reactors fare very well. There are well-established technologies. I don't know, probably some of you know that very well, but most of the reactors, and when I say most, it's really almost every reactor that we have running today around the world are light water technology, boiling water technology, or pressurized water technology. So it is a well-established technology, and the SMR based on this technology would be available, I would say, relatively shortly, in a 5 to 10 year time span, and definitely deployable in Estonia within the decade. So that's an important aspect. In terms of safety, and I will be talking again about every of the reactor. That was a strong requirement. We wanted that all the chosen selected SMR design would have some passive and inherent safety characteristic that would make sure that even if something happens, the safety function can be applied, can be performed without operator action, at least for a period of time that was higher than 3 days, and light water reactors achieve that. You will see later that the features of the X300 and of NewScale. In terms of load following, that's also an aspect that you will find for almost every reactors. We think it's an important feature into tomorrow's energy market, and so you see a trend appearing there as well. But of course, light water reactors operate at a temperature of around 300 degrees, 350 degrees at most, and so you can only go so far in terms of application to those markets that use low temperature steam, which might be different for our technologies. And then finally, I would say in terms of cost competitiveness, light water reactors, or at least the chosen light water reactors, fare well. They fare better than what we are currently seeing with the Gen 3 reactors. Of course, that was a strong need. I don't think everyone will contest that. But so we see that light water reactors as a whole are the family technology that will be ready shortly and that can bring some very promising prospects. Now, the other 3 families of reactors are a bit more exotic, I would say. They are part of the so-called Generation 4 technologies. Molten salt reactors, I would say that these are reactors that are very promising for the future. Unfortunately, with a lower technology readiness than the other technologies, but with very promising prospects. In terms of safety, I will mention it a bit later on because you'll see that light water reactors and molten salt reactors is actually what we've selected. In terms of application for the future, high temperature application, hydrogen production, petrochemical industry applications that are very promising, but also the prospect of bringing real long-term waste solution, being able to reduce the radioactive waste or long-lived radioactinides that are currently existing, and a cost competitiveness that is very impressive due to the compactness of those reactors. The high-temperature gas-cooled reactors have also very good features, but I would say what is a bit of an uncertainty regarding high-temperature gas-cooled reactor is the cost. We actually, in our current assessment, don't think that those are the family of reactors that can, under certain, talking for the selected design, we don't think that they can bring a very competitive cost compared to the first 2 categories. And then we have sodium fast reactors, promising in terms of waste reduction, again, but I would say that bring inherent complexity due to the use of sodium. Most of you probably know that sodium is violently reactive with air and water, which brings some challenges in terms of the design. You can make a sodium fast reactor very safe, but of course you need to engineer systems in a way that the primary coolant is sealed, and that brings some complexity, both in terms of operational aspects and so cost, but also in terms of what are the applications you can use them for and what you can couple sodium fast reactors to. All right. So to summarize very briefly what I've just shown you, we started from 50 SMR designs and applied a list of exclusion criteria that allowed us to reduce those 50 designs to a list of 13. Those 13 designs were assessed based on 7 technico-economic criteria that you can see around the wheel around there. And the results of this is that we've established a list of 4 top-ranked designs that are, in our opinion, very promising option for Estonia. I should say that those options do not compare exactly on the same foot. And what I mean by that is that we have the short-term deployment options offered by light water reactors, which is a well-established technology, and that could be deployed within this decade. And we have long-term sustainability options that I would say is a look a bit further in the future, for the next decade, most probably. Beginning mid-decade, well, we can debate, and I'm sure there will be some question around that. But at least technologies that can bring new, exciting features, waste reduction, as I mentioned, but also deep decarbonization of energy sector by the high-temperature process heat applications. So let's now focus a bit more on the selected and chosen design. So what I can say about the light water reactors, the 2 light water reactors, is that they are very different. One is the NewScale design, is a pressurized water reactor that is built in modules of 60 megawatt, and you'll see in the next slides how those modules are actually assembled in a common pool in patterns of 12 modules within the same unit. And in terms of cost, that is quite cost competitive if we compare it to the Gen 3 reactors. Just to give an order of magnitude, for the Hinkley Point C project, so not the first Gen 3 reactors, but for the Hinkley Point C project, we are at a capex of around $7,500 per kilowatt. So probably a high competitivity, but a competitivity that is even beaten by the boiling water reactor of Hitachi, the X300. A boiling water reactor of 300 megawatts that is very simple, in fact, in its design. It's very compact and simple. I will show you a picture. And that makes it also a very competitive project and interesting technology for Estonia as an energy future. So just a couple of things on the NewScale design. What you can see here is that the NewScale design really is different from what we know in the current pressurized water reactor technology. I don't know if there is. So the metallic vessel you can see in the pools are all containment vessels. So basically, what is contained in those metallic vessels are really the whole reactor. The whole reactor building, or almost the whole reactor building that we see in a PWR. So, if during the question I can come back on the old Kylioto project and show you the difference, but it's quite impressive. And those reactors are put in by 12 in a pool. They are factory built and shipped on site. So that's also a new way of constructing and building a nuclear power plant that brings some interesting prospects. NewScale has a very interesting features in terms of flexibility. They can go as low as 20% of the power load, and so one of the characteristics that they've embedded in their design is the ability to load follow renewables energy and to really be able to balance the intermittency of energy in the upcoming market. And last thing I want to say, technical thing I want to say about NewScale is about its safety features. I won't go into too much details about the safety feature of NewScale, but what they've managed to achieve is what Philippe introduced, and they call it the triple crown of safety, which means no operator actions, no backup power, and no water inventory required during the first 30 days of any accidental or any incidental scenario. So it is an achievement specifically considering that it's a PWR. Last word on NewScale. It's a technology that is becoming quite mature. They are undergoing the licensing process of the US NRC for the moment, and they will have their design certification by probably end of this year, and are looking at building a first-of-a-kind reactor in Idaho in 2026. Moving to the X300, I would say that, again, the real beauty of the X300 can be found in its simplicity of design. It's a very compact design, low cost, that is based on well-established technologies, and so we can also be very confident, I would say, in the ability of GE Hitachi to deliver this product to the market, because it is based on features of the ES BWR that is already certified in the US, and on the know-how acquired to the building of a BWR. So it is something impressive. The reactor is completely underground, and in terms of safety, they can also achieve this inherent or passive safety that can ensure no operator action, no reliance on backup power, and no need for additional water inventory for the first 7 days. So I would say that's a bit of the difference between the two, but that is very balanced by the cost competitiveness of these reactors. In terms of maturity, and the GE Hitachi people are in the room, so feel free to ask them about the reactor afterwards, but it's a design that is currently undergoing the pre-licensing of the US NRC and of the CNSC, so the Canadian Nuclear Safety Authority. So a focus now on molten salt reactors. I will be much more quicker on molten salt reactors, but I wanted to say a few things. First, in terms of safety, molten salt reactors bring something completely new. You have to know that molten salt reactors use liquid fuel, and in the molten salt, so liquid fuel, no pressure. To give you a comparison, a light water reactor, boiling water reactor is around 75 bar. A pressurized water is around 150 bars. This brings its own complexity, I would say, in the plant. No pressure in a molten salt reactors. In addition to that, the molten salt have the ability to have chemical retention of fission products that would make things so that even in the worst imaginable scenario, the radiological consequences of an accident would not impact the off-site area. So impressive features. And we have here two different molten salt reactors. The Moltex design is a 300 megawatts design, fast spectrum, so focused, I would say, more on being able to recycle spent fuel. Basically, that's their business model. Whereas the Terrestrial Energy IMSR design is more focused on bringing the product as soon as possible to the market, with reusing the most of the existing, which is very little experience with molten salt reactors, and so they use a graphite moderated molten salt reactors that is thermal spectrum. If we make a focus on this, as I mentioned, they bring new solution in terms of process heat application, and that is based on the fact that they can output a power of 650, not a power, but a temperature of 650 degrees, and so this high temperature steam really opens new areas of application. Heat storage that can again, be a game changers in flexibility. So the first two reactors we've seen had flexibility built in, but this is really a completely different level, and high temperature process heat applications. The IMSR design by Terrestrial Energy, in terms of maturity, is probably the most mature molten salt reactor that you can find on the market right now. And this is partly due also to the fact that they've made some choices in the design that are quite, I would not say conservative, but at least oriented towards rapid time to market. And for instance, they use graphite-moderated core units that are replaceable every 7 years. So we know that corrosion issues have been a problem with molten salt reactors, and to avoid that, they make a short lifetime of the reactors, and those reactors are replaced every 7 years. What you can see here is actually the core units in the building, and we can see that, well, I'll show you during the question and answers if you want to, but we can see here a core unit and the spent core units that are also stored in the reactor building. Then the molten salt reactors of Moltex, the stable salt reactors, again, as I mentioned, its main feature is a waste burner, so it reuses spent fuel as a fuel to reduce, I would say, the lifetime of radioactinides, but also to power its reactors. So a very promising feature, I would say, for the future of energy. In terms of maturity, I didn't mention about Terrestrial, but both reactors are looking at first of a kind in Canada around the 2030s. Currently, Terrestrial, so the Terrestrial Energy is undergoing the vendor design review of the Canadian Nuclear Safety Commission. They are in phase 2. Moltex is in phase 1, a bit behind. But they have a site already identified on which they would like to build in the early 2030s their first of a kind. I will just show you this picture to see why molten salt reactors are so cheap, because that's one of the things I mentioned, and it has to do mostly with the size. Basically, you compare a 1 gigawatt reactor of Moltex and the AP1000, you see directly the difference in size. It makes pretty much the cost. In addition to that, you have to take into account also the system design simplicity, but I think that gives a good picture. And I wanted to finish the presentation of the reactors on what is this feature of heat storage that molten salt reactors can bring to life. Basically, you can run the reactor at full power every time, store the heat, store the energy in the form of heat, and deliver electricity to the market only when electricity is needed. So when there is no wind, when there is no sun, you produce electricity at that time, and the energy you produce in the meantime is stored. So it's not like with the other reactors where you have to decrease the power. There you can really produce the full amount of power and just release it to the grid when it is necessary. And we've seen in economical study that this feature has some real value. So I wanted to, if I want to conclude this presentation, there is 5 things that I would like you to take away from this presentation. First, there is a strong international momentum around small modular reactors. The nuclear industry is on the verge of building demonstration SMR projects in several parts of the world, and the SMR technology is seen as more and more as a promising technology. The second one would be light water reactors are deployable within the decade. So we have technologies that are not long-term prospect that will be built in the coming years, and that represent an option for Energia, Estonia's energy future in this decade. The third one, long-term sustainability is achievable for nuclear reactors, and we see that the full potential of new nuclear can be achieved by those molten salt reactors that will arrive at the beginning of the next decade. Fourth one, SMRs can really be promoted together with renewable energy. And I think that's, I don't know what is the case in all the countries, but what I see in Europe is clearly sometimes there is a bad perception of nuclear energy as a competitor to renewables. This is not the case for SMR, and that's very important. And lastly, last but not least, I would like to congratulate Fermi Energia and really say that their ambition, their leadership on the market and their dynamic approach really brings something new to the nuclear industry. We see that it has drawn attention on the nuclear, international scene, and we really believe that it can become a trendsetter for the European nuclear industry. I'll leave you on this final thought before we take a couple of questions, just by saying, citing the International Energy Agency director, who said, there is no sustainable energy future in the absence of nuclear energy. Thank you.